Welcome to the debate. Imagine a scene right now, deep in the Amazon basin. A local healthcare worker is holding a solar-powered tablet.
Right, out in the middle of nowhere.
Exactly. They take a digital X-ray of a patient, feed it into the device, and, well, without any internet connection to a server in California or London, an artificial intelligence instantly flags early-stage tuberculosis. And it does it with the precision of a globally renowned specialist.
It sounds like the ultimate triumph of medical equity, honestly.
It does. But, what if the underlying mathematics powering that diagnosis has a foundational blind spot for the very patient sitting in that room?
Yeah, it's a profound tension. I mean, we are looking at a transformation in how we map the human biological machine. And the sheer scale is staggering.
Truly staggering.
Artificial intelligence is fundamentally rewiring global healthcare, crunching petabytes of data, from fragmented electronic health records to complex gut microbiome assays. And it's doing this to predict and diagnose disease in seconds rather than months.
Right. But that massive scale brings us to a critical inflection point, which is our central question today. Does the deployment of AI in medicine act fundamentally as a democratizing equalizer that bridges global health divides? Or
do its immense data requirements and algorithmic opacities risk amplifying existing health disparities?
Precisely. And my position is that AI is the ultimate equalizing force, bypassing human bottlenecks and physical resource scarcity to scale expert-level predictive and diagnostic care globally.
And my position is that, building medical systems on historically skewed data sets, siloed infrastructure, and mathematically opaque algorithms threatens to create a really dangerous two-tiered system of global health.
Let me start by outlining why I see this as an unprecedented equalizer. For centuries, traditional medicine has been defined by extreme physical scarcity. We simply do not have and will never have enough human specialists to review every pathology scan or, analyze every subtle metabolic marker for all 8 billion people on Earth.
That's certainly true.
AI shatters those constraints. By leveraging tools like convolutional neural networks, we are moving from reactive firefighting to proactive guardianship. And it's important to understand how these networks actually work. A convolutional neural network doesn't look at a gigapixel pathology slide the way a human doctor does, getting fatigued after a 12-hour shift.
Right, it doesn't need sleep.
Exactly. It breaks the image down into tiny overlapping receptive fields, mathematically scanning from microscopic pixel gradients that indicate disease long before human eye could detect a morphological change.
I mean, the mechanics of it are fascinating.
They are. Look at what Google's DeepMind algorithm accomplished. It can predict type 2 diabetes up to 3 years in advance using simple retinal fundus images, achieving, I believe, a 91% accuracy rate.
Which is incredible.
It really is, because the retina is a direct window into the microvascular system, right? And the AI can detect pixel-level degradation that correlates with systemic medical collapse years down the line. Because this relies on simple eye scans rather than invasive biopsies, it is technology deployable in remote Indian villages or Brazilian favelas. The core thesis here is that AI acts as a super forecaster, democratizing access to precision medicine regardless of geographic boundaries.
I hear that, and the technological promise is staggering. I readily concede that. But that promise is incredibly hollow if the foundational data is flawed.
Okay, how so?
Well, medical AI requires massive, high-fidelity datasets to identify those subtle, pixel-level correlations you just mentioned. But an AI only learns what it is explicitly fed. If you train an algorithm predominantly on Western, Eurocentric data, it learns Western, Eurocentric phenotypes.
And
this isn't a theoretical warning, right? It's a structural reality. We saw this vividly when a 2024 MIT audit found that U.S. skin cancer AI models were underperforming by 20% on darker skin tones.
Right, that was a major story.
Yeah, and why did that happen? It wasn't just a glitch. The models were trained on datasets where the mathematical pixel contrast ratios, the difference in color between a lesion and the surrounding skin, were optimized for low melanin skin. When the math was applied to highly pigmented skin, the algorithm literally couldn't see the edges of the melanoma. The baseline variables were skewed from the start. Deploying these mathematically flawed algorithms to the rest of the world doesn't democratize care, it exports clinical blind spots and deepens inequity under the guise of objective mathematics.
I see why you think that, but let me give you a different perspective. I completely acknowledge those early data paradoxes. I mean, if you train an image recognition model exclusively on fair-skinned Scandinavian patients, it will absolutely fail in sub-Saharan Africa.
Right, catastrophic failure.
But the solution to that exact problem is already scaling globally. We are no longer limited to isolated local data sets. We are using an architecture called federated learning.
Federated learning.
Yeah, and let me pause here, because if I'm listening to this, I might be thinking, wait, how can an AI learn from patient data in Brazil or Singapore without those hospitals actually handing over their raw, highly sensitive patient files to a tech company?
It sounds like a privacy nightmare on paper.
Exactly. But what we're really talking about with federated learning is fundamentally different. The central server doesn't collect patient files. Instead, it sends the AI model directly to the local hospital. The AI trains on the local data, learns the local physiological patterns, updates its internal mathematical weights, and then sends only those updated mathematical rules back to the central server.
It shares the insights, not the raw data.
Precisely. Think of federated learning like a global medical board. Doctors from every continent sit in a room and share their diagnostic rules and physiological insights without ever once sharing a specific patient's chart. Doesn't this specific architecture inherently protect marginalized groups?
Well,
I mean, it respects strict privacy laws like GDPR in Europe or Brazil's LGPD while still extracting the universal physiological truths we need. Right now, the Pan-UK Biobank is federating with Singapore's SG100K and Brazil's 100,000 Genomes project to train AI on 1.5 million genomes. Through adversarial training, where one part of the AI constantly challenges another part to find and correct its own blind spots, developers are aggressively de-biasing these tools. It captures a vastly broader genetic and metabolic diversity than we've ever had access to in human history.
I'm sorry, but I just don't buy that. Let me tell you why.
Go ahead.
Federated learning is a brilliant structural patch for data privacy. I'll give you that. But it is not a cure for missing data. You can only federate data that actually exists and is properly digitized.
Okay.
Whereas we are dealing with massive, structural data silos. You have Europe's heavily fragmented electronic health record systems clashing with China's deeply unified platforms. But more critically, low and middle-income countries often lack digitized health records entirely. You cannot computationally optimize your way out of a void.
But isn't the mobile revolution changing that? I mean, digitization is accelerating.
It's starting to, sure, but look at clinical nutrition, which is highly localized. Early U.S. AI systems designed to predict glucose spikes drastically underrated the nutritional needs and metabolic responses of rice-heavy Asian diets.
Because the baselines were off.
Exactly. Because the U.S. algorithms assumed certain physiological baselines built around a Western diet. If the local genomic data, the local microbiome profiles, and the local dietary responses haven't been captured, sequenced, and digitized in the first place, federated learning just creates a highly sophisticated, mathematically pristine echo chamber of the global north. You are still inherently leaving out the rural populations whose data has never been logged into a biobank.
Well, your point about rural populations actually transitions us perfectly from how we build these models to how we deploy them in the physical world.
Right.
You're completely right that pulling data from a massive Brazilian biobank doesn't automatically help an unmapped rural village if we rely on traditional infrastructure. But that assumes we still need the village's data to be constantly sent to a massive cloud server. We don't. We are shrinking the AI to fit the village.
You're talking about edge computing.
Exactly. Edge AI. AI doesn't need a billion-dollar hospital to function anymore. Through computational optimization techniques like model pruning and quantization, the landscape has completely changed.
It's impressive tech, yes?
It is. We essentially take this massive brain-like mathematical structure and surgically snip away the millions of connections it doesn't actually need to make a specific decision. That's pruning. Then we use quantization to compress the precision of the math itself.
Making it light enough to run locally.
Precisely. Suddenly, a neural network that used to require a warehouse of servers can run locally on a smart device. Like we said at the start, GE Healthcare's Edison AI platform is right now processing tribal X-rays for tuberculosis on solar-powered tablets deep in the Amazon basin.
Yeah.
And during the 2024 monsoon floods in India, Butterfly Network deployed portable ultrasound devices that interpreted cardiac echoes in refugee camps. It processes sound wave reflections locally on the chip, detecting rheumatic heart disease in children in seconds. This completely bypasses the need for high-speed internet. It's happening right now at the edge.
I come at it from a different way.
All right.
A solar-powered tablet running a compressed neural network is an incredible feat of engineering, but it doesn't fix the underlying hardware chasm. Let's look at the actual infrastructure reality. Sub-Saharan Africa has roughly 0.1 MRI machines per million people.
Wow.
The United States has 40 per million. You can have the most brilliantly pruned algorithm in the world, but if you don't have the magnetic resonance imaging machine to capture the tissue density in the first place, the AI has nothing to analyze.
Well, true, but...
And furthermore, when we look at advanced predictive models, particularly the ones modeling metabolic health, cardiovascular risk, and clinical nutrition, they rely heavily on real-time continuous data streams. We are talking about continuous glucose monitors and Apple Watches feeding edge AI on smartphones to predict insulin resistance spikes.
Right, wearables.
Yes, there are 2.6 billion people offline globally right now. Without the foundational infrastructure to capture the biometric data, we are essentially tailoring elite precision medicine for the connected wealthy and leaving the rest of the world behind.
That's an interesting point, though. I would frame it differently. Infrastructure is absolutely a challenge, but demanding global parity in MRI machines or wearable tech before we celebrate AI's impact is a trap.
A trap? How so?
We don't have to wait for perfect infrastructure to see massive democratizing effects. Consider Quare.ai's QXR deployment in 50 Indian district hospitals. They didn't install new multi-million-dollar imaging suites. They used basic, existing legacy X-ray machines.
Right.
Times grainy scans, the math was able to spot subtle consolidations in the lungs that the human eye missed on a low-resolution film. They boosted tuberculosis case finding by 50% at 1/10 of the traditional cost. If we can squeeze 50% more life-saving diagnostic power out of cheap legacy hardware that's already sitting in these clinics, isn't demanding perfect, globally ubiquitous infrastructure the enemy of immediate life-saving good?
Well, it's not about demanding perfection. It's about acknowledging that the physical deployment reality heavily dictates the clinical outcome.
Okay.
If you supercharge an outdated X-ray machine with AI, you still need a health system robust enough to action that diagnosis with antibiotics and follow-up care. But let's put the hardware aside for a moment.
Sure.
Let's assume the tablet is charged, the old X-ray machine works, and the model is deployed. We still hit the final, perhaps most difficult hurdle of all, which is what happens in the clinic, in that quiet moment between the doctor, the AI, and the patient.
Ah, yes.
This brings us to the black box nature of neural networks. Clinicians in Nigeria have rightfully balked at opaque metabolic predictions that provide a severe risk score but offer absolutely zero biological rationale.
You're referring to the explainability problem, the idea that the math is too complex for human auditing.
Yes, exactly. Let's look at a multiomics graph neural network. This is an AI that takes a patient's genomic sequences, their gut microbiome data, and their wearable step counts, and maps them as nodes in a massive, interconnected mathematical web.
A massive web of correlations.
Right. If that model predicts that a 50-gram spike in quinoa will severely dysregulate a specific diabetic patient, or it dictates there's an 88% chance of non-alcoholic fatty liver disease progression, the clinician needs to know the biological why.
Right.
But the AI can't tell them. It just spits out an 88% probability based on billions of calculations. If the AI cannot explain the causal biological pathway it used to arrive at that percentage, it deeply erodes clinical trust. In traditional medicine, a physician must understand the rationale before prescribing a life-altering intervention. Asking them to follow the machine blind is a massive leap of faith.
But the technology is rapidly evolving past the black box. I mean, we are not just accepting opaque answers anymore. We are developing sophisticated explainability tools precisely for this reason.
Tools like what?
Take a tool like GradCam, for instance.
It fundamentally changes how doctors interact with AI. When a convolutional neural network flags a pancreatic lesion on a scan, GradCam tracks the mathematical gradient flow backward through the network to see exactly which spatial regions of the image activated the decision.
So it works backwards.
Exactly. It essentially reverse engineers the math to overlay a thermal-style heat map onto the scan. It shows the clinician exactly which pixels and which textures the AI weighed most heavily. The AI isn't just spitting out a number anymore, it's highlighting its homework. Furthermore, the World Health Organization's Global AI Ethics Initiative now explicitly mandates these transparent, auditable models. When used correctly, AI doesn't replace the clinician. It serves as a super forecaster that empowers human oversight, elevating a general practitioner to a highly specialized diagnostic strategist.
That's a compelling argument, but have you considered that a heat map is a visual correlation, not a mechanistic explanation?
How do you mean?
Highlighting the pixels that triggered a diagnosis of a pancreatic lesion tells the radiologist where the machine looked, but it doesn't explain the multi-layered mathematical transformations that actually led to the conclusion.
Well,
It's like having a brilliant savant diagnostician who can look at a patient and tell you instantly they have a rare liver disease. But when you ask them how they know, they just point at the patient's abdomen and stare at you.
okay, that's a funny visual, but
The multi-omics example we just discussed, a heat map doesn't even exist. If an algorithm fuses genomic data and satellite imagery of food deserts to predict an obesity trajectory, the sheer dimensionality of that math is fundamentally beyond human comprehension. We are asking doctors to blindly trust an algorithmic oracle.
I'm not convinced by that line of reasoning because, well, traditional medicine already relies heavily on empirical black boxes, and we accept it every single day.
Really?
Yes, we prescribe medications like acetaminophen for pain or lithium for bipolar disorder, where the exact complete mechanism of action has been debated in the literature for decades.
That is true.
We don't perfectly understand the why, but we use them because empirical, rigorous clinical trials prove that they work. Why must an AI that consistently surpasses human radiologists in spotting fatty liver infiltration or correctly anticipates a metabolic crash be held to an impossible standard of perfect mechanistic transparency? If a clinical trial validates that an AI dietary model safely reduces HbA1c in diabetic patients by 1.5%, the empirical outcome should validate the tool just as it does with the novel pharmaceutical.
The double standard exists because the failure modes are entirely different.
In what way?
When a pharmaceutical fails or causes an unexpected side effect, we have biological frameworks, chemical assays, and physiological pathways to investigate why it happened. We can isolate the variable.
Okay.
When a multi-dimensional neural network fails, we often have absolutely no way of knowing if it failed due to a rare biological edge case or because the patient's demographic data triggered a hidden systemic mathematical flaw deep in the weights of the model.
Ah, I see what you're saying.
That distinction is critical. It is the difference between an honest, isolated medical error and formalized discrimination embedded in silicon. If we can't audit the math, we can't fix the underlying flaw.
Which brings us to a crucial moment of synthesis. If we look at the totality of what we've unpacked today, my position stands that despite the genuine infrastructural gaps and the valid clinical trust hurdles, AI's ability to decode complex gigapixel exams in seconds is revolutionary.
It is revolutionary.
Right. By utilizing edge computing techniques like model pruning to bypass poor internet, and by modeling multi-omics data to find hidden diseases, we are looking at the greatest leap toward global health equity in a century. It allows us to fundamentally bypass the physical scarcity of medical experts. We can now deliver top-tier, globally informed diagnostic insight to the most remote corners of the globe, shrinking the gap between a world-class research hospital and a rural clinic.
And my concluding view is that we cannot allow the sheer brilliance of the mathematics to blind us to the physical realities on the ground. Algorithms, no matter how compressed or optimized, cannot outpredict poor infrastructure.
Right.
A predictive model is only as equitable as the hardware running it and the data sets training it. Without aggressive, rigorous debiasing of those foundational data sets, and massive, sustained investments in accessible physical hardware like imaging machines and biosensors, we are simply taking the health disparities of the physical world and encoding them permanently into our digital systems.
Yet I think we both find strong convergence on one immutable fact. Human oversight remains utterly irreplaceable in this equation. The AI is a tool, a high-powered lens, not a standalone doctor.
Absolutely. And that human oversight must be truly global. We both see the absolute necessity of open-source repositories in this fight.
Yes, definitely.
Platforms like MONAI for medical imaging or Hugging Face hosting metabolic prediction benchmarks are vital. They invite coders and clinicians globally, from Tel Aviv to Tokyo, Nairobi to Nanking, to audit the math, challenge the models, and build localized solutions. Transparency and open collaboration across borders are the only ways to build clinical trust and spot those mathematical blind spots before they reach a patient.
The tension we are discussing today between rapid, life-saving innovation and the cautious, rigorous validation demanded by humanity's incredibly diverse biological tapestry is truly the defining medical challenge of our era.
It really is.
As we look forward, tools like generative AI and digital twins, virtual replicas of patient metabolisms where we can safely simulate infinite diets and treatments before prescribing them, promise even deeper insights. There is vast complexity still left to explore in how we map the human machine.
Indeed. The technology will only accelerate from here, and the questions will only get harder.
At the beginning of our discussion, we talked about the shift from a doctor observing a single X-ray on a light box to a network crunching petabytes of global data in seconds. For the first time in human history, doctors are armed with logic that exceeds human computational limits. The ultimate question moving forward isn't just whether the machine can spot the disease faster than we can. It's whether the machine, trained on the entirety of human data, sees all of us equally when it looks. Thank you for joining us, and we'll leave you with that to consider.